Hi there, today I'm going to be talking about a new GUI designed to run the Volcanic Event Age Model, or VEAM. This is a model that was developed at the University of South Florida by James Wilson for his master's project and some other people that you can see in the list on the right to get a potential age range for volcanoes in a volcanic field on Earth and on other planets. So on the left, you can see the basic empty just run it GUI, and on the right, here's a paper that we've published using the code that's written by James Wilson. So I'm going to go through how to run VEAM through this GUI, some of its features, and some of the changes, the minimum changes that we've made to the code to make it more adaptable for a graphical user interface. So let me close out here, and we'll come back to this later. And right now I have Spider opened. This is just my Python development environment of choice, and here's the Python GUI script. Here's an outline of the script. And let me collapse that here for you. So the code that James Wilson originally developed opened up a configuration file, ran the age model, came up with many simulations, as many as you want, wrote some stuff out, and closed. And this does the same thing. The major differences here are in this outline that you can see that we've taken some of these VEAM functions that James originally coded, which are still there, but we've removed some of them and placed them into this event library structure or class, which allows this code to be more object-oriented. One of the main components of VEAM is that it sorts events randomly or according to a user-defined preference for each simulation. And instead of that being a separate function, we now have it in the event library here as different methods. Now, the event library stores different volcanic events, which are their own separate class now. Below, so we have VEAM functions that are nearly identical to the original VEAM code. We have VEAM variables and structures, which are a slight retooling of the original code, and then we have these GUI windows down here in this code. Now, this code does have several requirements. Most of these are things that we generally have on our own Python, or on any Python installation. This includes sys, os, time, and operator, Skippy or SciPy, NumPy, and Matplotlib, which are generally found on computers that do Python with earth science. And then to make the GUI, we use PyQt5. In order for the GUI to continue to run while VEAM is actually simulating events, we use threading. So these are also involved. Now, this GUI, or this script, was created in Python 2.7. So you'll have to make sure that you have all of these and Python 2.7, but I hope that shouldn't be too hard for you. So let's just do a quick run through here in Spider. So I'm going to go and play this and bring that window up to the front, and you can see here that I have my IPython console here that prints out just a couple of things as VEAM runs. But right now we have our event age model here as the GUI. So we can go ahead and fill this out, and after we fill it out, we can check the inputs to see if there are any errors. So say I have a volcanic field, and I know some ages and I know some stratigraphy. But I want to know what the recurrence interval is lately. So I'm going to say that our volcanic age for the entire field starts at today. And then maybe our maximum possible age for the entire field. This isn't the maximum possible age you're interested in, but the maximum possible age you feel that volcanoes can possibly be. Well, let's put this back at million years, and let's say that it could be maybe 10 million years old. Then we have that the oldest event that we have in our database is 10 million years old. Now let's say something about the temporal resolution that VEAM works upon. This allows VEAM to have a cumulative distribution function that has bins every certain number of years. So let's change this to 1,000 years. So maybe 1,000 years, or maybe how about half 1,000 years? So every 500 years, it'll come up with a new result when we actually plot it. Now for this age database path, we can go in and select any database that we have. Here I have a couple of age databases. Let's go into here, and maybe we can select Mount Lassen age database. And then we can select a stratigraphy database too. Now if you have a different stratigraphy database, you can of course modify this and say maybe Lassen strat db1.dat. That should work. And then you have to have a number of simulations. This has to be at least one, but it can be as many as you want. Maybe let's go with 100 for now to show you 100 simulations. And then you have to choose a sorting style. So sorting styles were defined by James to more efficiently or more accurately come up with the correct age or the correct recurrence rate of each field. And this ends up being based on your data, so you have to kind of choose it correctly if you want. But generally, however you sort it, say least age uncertainty, that means that the volcanoes with the least age uncertainty in your model will be dated first in every simulation in VEAM. If you do most stratigraphic contacts, then it will be in the stratigraphic database. The event with the most relationships will be dated first. If you choose ignore stratigraphy, then this database path will be opened and loaded, but ultimately ignored, and it will only use ages. If you choose random, then it just randomly sorts and randomly dates your or dates your events in a random order. So let's just choose one. Let's say random maybe, and then we can check some inputs. And as you can see, it checks for errors. So I've cleverly renamed our strat database file to something that doesn't exist. So if we take out this one, this should be an accurate file again, or an existing file again. We can check the inputs, and we can see that no errors are identified. Now, one other thing about this GUI is that you can actually save the configuration as whatever you'd like. So we can go to example, and we can save it as perhaps example.txt, and that will be saved. So it says configuration saved. And even if you have errors in this, you can still save your configuration for your own debugging. And then once you have a valid configuration in this GUI and you save the configuration, you can run this configuration using the original veam.py script that James Wilson developed, and it should still run and give you what you want. So of course, if we don't want these, we could instead say load a configuration file. So here I'll load this configuration file that I already chose. You can see our configuration file that we just picked. Let's open up this one, and we have Lassen database. You can see that this now has loaded everything, and it's changed our units back to mega annum. So we have 0, 3 million years, and then a temporal resolution of, it looks like 10 years. And these are our database files that we just used, and it's only going to have 20 simulations and sort by most stratigraphic contacts. So then we can check the inputs, and we have no errors identified, and we can run VEAM. If, say, you ran VEAM with some error, so you have, this is not a number, if you try to run VEAM, it will not run. So let's make sure that's good and run VEAM now. No errors, And you can see that with 20 simulations, it goes relatively quickly along the progress bar, and now we can see some results. So here's the result. It's just a simple cumulative distribution function of the total events in your field over time. So at the beginning, at 3 million years before present, we have no volcanic events occurring, and that rises to this maximum of 131 events that are in our field. Now we can save this figure and save data, but I'm going to do that in a little bit. Right now I'm going to close this, and I'm going to show the example that we gave in our EPSL paper for RCA mods. So let's go ahead and load that configuration. That's at arcia.cfg in this example directory. We can open it. Now we have up to 1 billion years, 1000 megaannum, with a temporal resolution of still 10 years. And these are the databases that we used at the time, and we counted, we developed our age models based on crater counting. So we want to date the ones that we feel have the most craters, or we feel have the least uncertainty for that crater age model first. And we're going to do 100 simulations here, or maybe we can ramp that up to maybe 500 simulations. And let's run VEAM again. So now it's running VEAM. Alright, let's see some results here. And it takes a little bit of time to actually plot 500 examples, but here it is. And now we can see this cumulative distribution function, which shows that the number of volcanoes in the field really doesn't start popping up until maybe after 250 million years. And then after 200 million years, the number of events per year really starts to skyrocket, and ultimately we have all of our volcanoes on the surface perhaps 50 million years ago. Let's try to save some of this data. We can save this figure. So let's save the figure in this empty results directory, and we'll save the figure as arcia1.png. So this figure can be saved as any raster format, or it can be saved as 3 raster formats: PNG, JPEG, and TIFF. So feel free to use whatever you want as your end, or as your file suffix, and we'll save that. And let's save the data as well. So the data here, maybe we can save it as arcia.dat, whatever you want again. And now you can see that the figure saved and data saved labels have popped up to show you that you actually saved these, and so we can close this out. Let's go again and let's say we want to ignore the stratigraphy on this one and see how that works. We can run VEAM again and show these results. Now, while VEAM is actually running, it's putting out a pretty sparse list of things. So down here in the console, you can see it's saying begin VEAM simulation. It's telling you it loaded all of the events in the age database, and it says it's loaded all the relationships, and ultimately it's completed 500 simulations in 1 second, or 1.5 seconds, which is pretty fast. Now you can see with these results in the ignore stratigraphy possibility that our cumulative event count with time has dramatically changed. So now we have a higher uncertainty. In the past, maybe more events happened earlier on, and that might really indicate how powerful stratigraphy is in understanding when these volcanoes actually occurred on the surface of your volcanic field. I'm not going to save these, or maybe I can save this data as, say, arcia_ignore strat. Why not? So that is the VEAM GUI right there. So we've saved a figure and we've saved data for the model that we are setting up in this GUI to run James Wilson's VEAM code. After this, I'll show you something slightly different to go from that data that we just saved to start to model the recurrence rate with a different Python script that does not have a GUI.